Hello everyone, this is Gary Marr from Arizona State University. This screen capture is from my IFT 101 class. And in the screen capture, I'm going to talk about some topics and concepts covered in Module 1. Now, this screen capture is just going to go through the PowerPoint slides, which I've already placed inside Module 1. And not to beat a dead horse here, but it's going to be the same material that you've read. And this is the same material that's in the PowerPoint deck. What I'm trying to do here is just accommodate different learning styles. Some people prefer to listen to a video or watch something as part of the learning of new material, and that's what I'm trying to accomplish here. So this is optional. If you've read the material in the textbook, gone through the assignments and labs and don't have any problems, then you're probably done. If you'd like to be able to kind of use this to refresh your memory or to reinforce some topics, that's fine too. If you want to use it later when you take the test as part quiz, as part of review, you can use it then. I will try to do one of these for each module. That's the plan anyways. And you'll see that I've sprinkled other videos in there, most of which I've done, some of which are available with Severance and some other resources that I've found on the internet. But this is the first one, and because it's the first one, just a reminder, make sure that you watch the welcome video, read the syllabus. This class is going to be built on PowerPoint slides, textbooks, assessments, and Python. It's online entirely, so we have to do everything through Canvas. If you have questions, send me a Canvas email. I'm usually going to get back to you within a few hours. There's also been 7 discussion questions set up in Canvas, 1 for each module. So if there's a particular question you have about an assignment or a lab on the module and you're trying to clarify it and you don't want to send me an email, you can always pose it on the discussion board, and other students might be able to chime in and help you out. Please don't put any solutions to assignments or labs on the discussion board. I mean, that's there to discuss problems, not to leave answers. Okay, so the way the course is organized. Sprinkle is going to be where most of the assignment information is going to be taken from. So when you sit down and do those assignments, you want to reference the Sprinkle textbook and the material and the glossary and the stuff there. The labs are primarily Python-based, so it's a combination between Severance, Python resources, but it's going to talk to topics that were covered in the Severance textbook, or excuse me, the Sprinkle textbook. The problem is the Sprinkle textbook is a general programming textbook. The concepts and topics covered could be used in any programming language, and Python is not part of the text. So what I'm going to do is fill in the gaps. I've got videos I'll fill in the gaps. I've got PowerPoints that'll hopefully fill in the gaps. But what I want to do is teach you guys Python and relate it back to the models that we'll build in Sprinkle. And if you think about the order of things here, and this is pretty well established in Sprinkle, you've got algorithms, which are really just rough ideas of how the logic in the program should work. And then you have flowcharts in Pseudocode, which are more formal logic models. And the intention is to take those formal logic models, use a programming language like Python to create the program. That's the sequence of things. And we'll be doing all of those in this class using the Sprinkle textbook and outside resources on Python. The Python we'll cover is a basic knowledge of Python. It's by no means extensive. We're not going to get into object-oriented programming, and we're not going to do a lot of advanced Python topics. But we're going to get you started with a very good programming language that's fairly easy to learn and fairly powerful. Very popular right now also. Excuse me. Now, the textbook starts off like a lot of programming textbooks, discovering what's called SDLC, System Development Lifecycle, or a problem-solving methodology. And essentially what this is a waterfall approach. And what that means is one of these phases drips into the next phase, drips into the next phase, drips into the next phase. And when you do all of these 6 steps, you will have satisfied a problem or opportunity that you needed to solve. I've had students call this the scientific method. It's been known SDLC for me since I started. It's used by programmers, network people, cyber people, pretty much everyone, and I would argue it's just common sense. The steps that you would follow in this process would be very similar to ones you'd probably follow if you're buying a new car, buying a textbook, deciding where you're going to go on vacation. All right, you're going to look at what the problem or opportunity is. You're going to research it. You're going to identify some alternate ways to be successful. You're going to pick the best of those alternatives. You're going to model it and implement it. and then you're going to evaluate it. And I think that probably buying a car or picking a travel location would probably be solved by following this approach. Now, one of the things about this approach is it's more or less a rifle or targeted approach versus a shotgun approach. It's cost effective, it meets the requirements, it's time efficient, and essentially what it does, you get you a reliable answer in the shortest period of time. If you think about the difference between a rifle and a shotgun, a rifle is a single shot, you take aim. If you're shooting at a target, you aim for the target. If you take your time to aim and prepare for the target, you hit the target. A shotgun, when it goes off, blasts pellets in all different directions. Some of the pellets might hit the location you want to hit, but a lot of the pellets will not. So it's not terribly efficient. It may be effective, but not terribly efficient, and nowhere near as effective as a targeted approach. The way I would illustrate that is a non-technical example. If you're trying to go to school and your car doesn't start, if you follow a targeted approach, then basically you'll look at the problem, the requirements, the analysis. Well, my lights and radio are working, so it must be a battery. Alternatives, and here are some alternatives I've listed for you. Some of these alternatives are fairly involved and expensive. Some are less involved and expensive. As you evaluate the alternatives, you will design the best solution. In this case, maybe it's just simply a bad cable. And by putting something to test that battery, it would show you the bad cable, and then you would replace the cable and off you went. Versus a shotgun approach. The shotgun approach would say, okay, my car won't start. Replace the engine. Replace the starter. Does this need gas? Replace the gas tank. All of those things could be viable alternatives, but probably if you did a little more investigation, a little more formal approach, you'd find they're not terribly practical. Either they take too long or they're too expensive. So we want to be very deliberate, process-oriented, and attack these problems in a very systematic fashion. That's a lot of Chapter 1, and that's a lot of what you will do as you work with technology, and I would argue as you pretty much do anything that involves a decision. Types of decisions, types of problems, I should say. Algorithmic, heuristic, algorithmic lend themselves very well to computer programs. Heuristic solutions are rules of thumb. I like that color white. I think that stock's going to do. I think the economy is going to crack. The economy is going to go up. They're basically gut decisions, not necessarily based completely on a set of data, but more a rule of thumb. These can also be programmed. They can be combined into a hybrid solution where part of the program is algorithmic and part of it is heuristic. You'll be asked in your first assignment to give some examples of algorithmic and heuristic solutions, solutions, okay? Spend some time, think about that some. Think about those kinds of the solutions that you go from your gut and those kinds which are very, very mathematical or very process-oriented. If you're going to balance your checkbook, for example, that's a very process-oriented algorithmic solution. Picking a stock to invest in might be more of a heuristic solution or a combination. Difficulties with problem solving. If problem solving was as simple as following those 6 steps, there would never be any problems in the world. Well, that's not the case. There's lots of problems that can crop up when solving problems. Here are some of these problems listed for us. I don't think this is actually specifically addressed in any of the assignments. This may come up. This might make a great multiple choice question, for example, on a quiz. Okay, so you want to find in the textbook where this was referenced, do some extra reading, see what they're trying to get at, if you have any questions. And always, if you have questions, you can always come back to me. Chapter 2. This is where we start to get more meat in the bones. It's a little bit longer. You're going to find that from Chapter 2 on, and we're not going to cover all the chapters in this textbook, but starting with Chapter 2, there's a lot more slides. I'm not going to probably cover all the slides. Some of them just are continuations of a process of solving a particular problem with an algorithm or pseudocode, but you're going to find there's a lot more slides from here on in. Chapter 1 was pretty light on slides, but the others are going to be a lot more involved. We start off with a discussion of identifiers. Identifiers are names you're going to create as part of your logic, which are going to reference memory locations in the computer. The computer keeps track of memory locations with hexadecimal addresses, something that's not going to be terribly easy to remember or even work with. So what we can do is we can give our identifiers names. Now, there's different kinds of identifiers, however. There's constants and there's variables. If something's constant, it doesn't change. All right, we do have situations where we have data that does not change. The classic example is pi. If we use a variable name that's a constant to identify pi, we know that value will never change, and that's fine. We need the value perhaps for a calculation, but hopefully we don't have to change it because it should not change. If you look at the example that I created for class, you'll see it in Module 1. It's a Module 1 example. I have a constant there, which is a location of a company. Okay, and that location value should never change in that particular payroll calculation I'm showing you guys. So constants don't change. Typically, when you build a name for a constant, you capitalize the entire name. So pi here would be capitalized PI. As opposed to variables. Variables by definition can change. So what you'll have here is either an application which may accept input that could be different each time it's run, or input that may change as calculations are made. This one here is accepting input of age, cash, city, zip code. If I wanted to somehow calculate this percentage increase in cash and then place it back in cash so I could print it out, I could, since it's a variable, take that original cash value, do some calculation against it, and store it back into cash because it's variable. It can change. I cannot change constants. Once constants are set, they're there, and they're supposed to stay there. They could be used in calculations. They could be displayed, but they should not change. Variables will change. And these are some of the basic building blocks of logic, and therefore some of the basic building blocks you're going to find in Python when you build your programs. Rules for naming conventions. Be consistent. There's a couple different conventions you can follow. There's snake casing, shish kebab casing, camel casing. You will see these in the programs that I create. You probably won't see as much of that in the severance text, but you want to be consistent and follow the same standard throughout your program. Here we have some different examples. This is one of the questions, I believe, in one of the assignments. One of the things you don't want to do with variables or constants is put spaces inside the name. It should be a series of letters. Now, the letters could be upper and lower case. They could be joined with underscores like we have here. They could be joined with dashes. Sometimes it depends on the language. I use camel casing, which is this last version over here, and the outer column here, where you start with either an upper or lower case for the first word, and if the variable needs 2 or more words to describe it, every subsequent word would have an uppercase letter marking the beginning of that word. So here we have hours worked, quantity per customer. Here's the underscore casing, and the shish kebab casing is not up there. That's just simply a dash between. Dash is not supported by all languages. Underscore and camel casing does work with all languages. Keep the names short. Don't make them too long. Okay, and you once you get in there and you can start to get your hands dirty with Python, this will probably be something you can address a little better there. And if you have questions, again, just ask away. But each language does have a little bit of rules that you'll have to follow. You can't, for example, create a variable or constant name that's a reserved word. Python, since it's an executable programming language, has reserved words. Words like if, while, print. Those are restricted to Python. You cannot use them for variable or constant names. This is your basic systems model. This is how a lot of software is created. You identify your inputs, and this is what you'll do in your pack diagrams also. You'll identify the inputs. You'll have some process on that input to create outputs. Okay. There's a basic diagram of that flow. Here's one's a little more specific as it might pertain to a balance, a checkbook balance. Excuse me. Pseudocode is how we typically, or at least how I like to be able to model my logic before I put it into Python or C# or Java. And essentially what it is English statements. It can be executed by the computer. And there's no real rules behind it, except that you should start it with a keyword start, and you should end it with a keyword exit or end, or at least have a comment in here. For this particular example, this isn't in the book, This has got some comment symbols in here. It's using the Python comment hashtag. And all a comment is, it's like a documentation line, which almost seems redundant in this situation because pseudocode can't be run. But what it tries to do is it tries to expand what I've done in pseudocode here with a more English-like definition of what's happening. And comments can either be before the line or they can be to the right of the line. Typically, it's never after the line. I do have a short page or short description of how pseudocode works in Module 1. You can go in there. It's not from this textbook or our textbook. It's from another class that I taught, and that hopefully will help you with pseudocode. But again, pseudocode, it's great for modeling stuff, but you can't execute it. But it's very close to programming code, and you'll see an example I've created for you guys from Module 1, how I take pseudocode and convert it to Python. So here's my pseudocode. In fact, I've got the example right here, one of the examples. Here's my pseudocode or my logic model. This is the stuff that I'm going to focus on in the Sprinkle book. And this is the actual Python program. This is what you'd likely to see in one of your lab assignments. Again, the assignments for this class will typically point to Sprinkle. The labs will point to Sprinkle and Python. Variables have data types. Typically, and this varies by language, but typically you'll identify your variables as being a number, letters, booleans, true or false. Okay. You can look through that. There's some examples here. I'm not going to read this out for you. You can see these yourselves. What I'm trying to do with these PowerPoints is identify the key summary items that you should walk away from with this particular chapter reading, and also what you might find in an assignment or a test. Symbols. This is where your calculations are built on. Modulo division is probably one you haven't seen before. That's simply the remainder if you do division. And that's important to determine if you've got an even number or odd number, for example. Logical operators are used in what's called Boolean expressions. Relational operators also. These are what build our if statements and our while loops, which we'll get in later in class. This particular table this is called the truth table. This will be built on in greater detail later on in the class. Same thing with this. You also have to deal with the hierarchy of operations when working with a computer. In other words, calculations, even though the operators may suggest that you're going to do math and then do division, because it's addition and then division. But since division has a higher priority than addition, division is done first. And let's see if we don't have any examples of this here right now. But if you look in the textbook, and this likely will be also a question on a test, if you have a situation where you have 3 plus 2 times 1, 2 times 1 is done first, then the 3 is added to that result. And that can change that can change the answer based on how you evaluate that expression. If you're using PEDMIS, which is the hierarchy of operations, you're going to get one answer because it's going to be based on that hierarchy. If you simply read it left to right, when you read it left to right, you could get a totally different answer because it's not looking at operators having a different level of precedence. Multiplication and division have to be done before addition and subtraction. The highest order is parentheses, and you can use parentheses to sometimes override that scenario. Okay, but I think the biggest problem most new programmers have is they forget that the division, multiplication are not or are the same priority as addition and subtraction when they're not. Multiplication and division are done first. All right, this is my first reference to severance. With the severance stuff, you can read the textbook as it stands. You can probably find the same information in a whole bunch of other sources on the internet. One of the nice things about Python is it's developed as an open source, free product. It's supported by Microsoft and Google, a whole bunch of companies. There's a lot of free stuff out there, and the severance book is I put it out there inside the class resources as a PDF, so you don't have to pay for anything. or you can actually buy the Severance book from Amazon. I think it's about $10, or you can watch the videos. But you can do whatever you want for Python as a reference to help you get through the Python code, and you'll also see some stuff that I'll provide. Questions? Okay, if you have questions, let me know. Go to the discussion board, send me a Canvas email, and look at the other sources I've placed, or the other resources I've placed in Module 1. Thank you.